Thank you very much, Michelle, for the introduction. I am honored to be able to stand here on the stage and talk to you about recent progress in utilizing GPUs for simulations of black hole accretion and jets. We have a large team that is headquartered in Berkeley. I will be soon moving to Northwestern, where I'm taking an assistant professor position. My collaborators include Matthew Lishka and Casper Hasp, who are graduate students and master's students in this room, Eric Coughlin, who is a postdoc at Berkeley, Nick Stone, who is a co-PI of this Blue Waters effort. He and Brian Metzger are affiliated with Columbia University. Because it's the first black hole talk of this meeting, let me briefly introduce the landscape of black holes to you. They come in two major flavors: the supermassive black holes, with masses ranging between millions and billions of solar masses. Those guys live at the centers of galaxies. For instance, our own galactic center hosts a 4 million solar mass black hole. And stellar mass black holes, with masses ranging between a few and a few tens of solar masses. Those are end products of lives of massive stars, and they occur in binary systems and during core collapse of massive stars. Even though the physics that I'm going to be talking about, it works irrespective of the mass scale of the black hole, I will be mostly focusing on the supermassive black holes. And these guys, they do a lot of havoc, wreak a lot of havoc on their environments. They can explode galaxies. You can see the center of the Perseus cluster, where the black hole is inflating bubbles and sending shockwaves into the ambient medium. In this dramatic example of M87 galaxy, we see the black hole is inflating the cavities and sending shocks as well. And this astonishing example of the cluster MS0735.6, the black hole is inflating two huge cavities via these collimated outflows, which we call jets. And what's amazing is that these jets are inferred to contain energy comparable to the entire rest mass energy of the black hole, or the maximally possible rotational energy the black hole can have. So that is straining the models of jet production. One difficulty in interpreting such observations is we don't know how much food or how much gas the black hole ate in order to produce these fireworks. It would be nice to find a laboratory where we would have more control over the black hole diet. And it turns out nature provides us such laboratories. These are called tidal disruption events. Those events happen when a star comes too close to the black hole. The black hole tidal forces tear the star apart, and half of the star falls into the black hole, half of the star is expelled. The one half that falls in, we know what the mass is. It's half a solar mass. So these sort of events offer us a very well-controlled, almost laboratory-like environment for studying observationally the process of black hole accretion and the formation of such marvelous outflows. However, there are difficulties in simulating those systems. And I'm going to come to this difficulty in a moment. The standard approach to black hole accretion modeling is we will put a black hole in our computational domain. We will direct its spin up because it's the easiest. And then we will feed some gas in the equatorial plane. Then what this system naturally leads to is to the formation of an outflow from the inflow. Some gas changes its mind and gets kicked out. This outflow surrounds the black hole-powered outflow part that is really coming from the black hole spin, and this is what we probably are seeing in the observations. However, this is not what we expect to happen in most of the black hole accretion systems. That's because the direction of the black hole spin doesn't know anything about the large-scale direction of the angular momentum that feeds the black hole. Therefore, what we would expect is that actually the inflow will be misaligned with respect to the black hole at some appreciable angle of order unity of order of 1 radian. And that makes understanding what happens in these systems physically much more challenging, both theoretically and computationally. In fact, we still don't know what happens to the outflow. Does it rotate together with the disk, or does it stay pointing along the direction of the black hole rotational axis? And this is the grand challenge that we're trying to address, the physics of these naturally forming the typical accretion disks and outflows around the black hole, and we would like to do so from first principles without making almost any approximations. In order to do that, we undertake the numerical approach, of course, since this is the Blue Water Symposium. In order to address these really hard problems, we developed a GPU-accelerated general relativistic magnetohydrodynamic code that we call H-AMR. It stands for HARM, which is the precursor to this code that we started the development of the code, and AMR stands for adaptive mesh refinement. So you can see more details on the code technicalities at the poster by the graduate student who is sitting here in the first row, Matthew Lishka, who is basically the developer of this code. He did 99% of the work himself, so I highly recommend that you seek him out and talk to him if you're interested in these sorts of simulations and the use of GPUs in accelerating grid-based and particle-based codes. In a nutshell, the code shows excellent parallel scaling to the entire Blue Water's GPU partition. A single GPU gives you a speed up between a factor of 100 and a few hundred, depending on the type of GPU you use, compared to single core of a CPU. So here is a more detailed bar chart. The one core of the CPU is here. It's one NVIDIA K20X GPU that the Blue Water is equipped with is 15 times faster than the entire CPU, or 100 times faster than a single core of the CPU. And the recently available Tesla P100 GPUs are a factor of 450 faster than a single core, which translates into 65 times acceleration compared to the entire CPU of the XK node, which is an astonishing factor of acceleration. At least in my view, we heard that there was acceleration by a factor of 10,000. This is nowhere near, but this is still pretty good for our applications. But that's not all. Matthew, in the past year, implemented adaptive mesh refinement together with the local adaptive time stepping, which is illustrated here. Wherever there is a structure in the flow that we need to resolve, we can add more cells, we can refine the grid, and put more resolution there. And that set of features allows us to study these typical tilted systems because we don't know where the disk will go. We don't know where we need to put the resolution, and adaptive mesh refinement allows us to not worry about this and automatically follow the flow. These features allow us to get an additional speed up of about a factor of 10 to perhaps 100, depending on the thickness of the accretion disk or a stream that we want to resolve. And that allows us to convert our 9 million GPU hour allocation on Blue Waters into something of order of 9 billion CPU core hour equivalent, which is, again, a really big number that I'm still trying to absorb. But the point is, whatever I'm going to be showing you later would not be possible without the use of GPUs. On the CPUs, we would never be able to do this. So with the large GPU partition, Blue Waters is perfectly suited. It fits our code like a glove and allows us to get great results, as hopefully I will convince you in a moment. So what we're trying to get here is a black hole revolution using Blue Waters coupled with H-AMR. So what's the physics that we're trying to study here? What are the expectations? What are our priors? Well, if we put a thick accretion disk misaligned with respect to the vertical axis of the black hole spin, then the torques due to the space-time dragging by the spin of the black hole would cause this disk to precess. So this is what you're going to see. In a slice, you will see the disk that's doing this dance, the precessing dance, and that's what I illustrate here. But the big questions remain. Nobody really simulated jets production by these precessing tilted disks. So we don't know if these disks even produce jets in the first place, and if they are produced, whether they follow the direction of the disk or the black hole spin. And see Casper Hasp's poster, who will talk more about the physics that comes out of the simulations, some of which I will describe in the next slides. If we go to a thinner disk, which naturally happens in tidal disruption as the mass accretion rate drops, the disk regains ability to cool and goes from this disk to that disk. What we expect is that the inner part of this thin disk will be brought into alignment by the so-called Bardeen-Peterson effect. This effect has been observed in pseudo-Newtonian simulations, which approximate the effects of general relativity, and at small inclinations of the disk, comparable to its thickness, not such a high inclination. In fact, at large inclinations like this, what the expectation is that the disk will break into independent rings, which would be a really important effect. And so it would be nice to see if this effect happens. So the big questions we try to address here is, if we have a thin disk, does it align with the black hole spin in GR, or does it not? Does it break or not? This is a challenge that is only possible by a combination of adaptive mesh refinement and the GPUs. So this is our first simulation result for and how much time do I have? Because apparently none of my timers are working.
You've got about 6 minutes left.
That's great. OK. So this is our first simulation of a thick disk that we tilted with respect to the vertical axis by the angle of 30 degrees. This is a pretty thick disk with the aspect ratio of order unity. The black hole is spinning with a spin of about 0.9, so the spin is vertical. This is a zoom in of the right panel, and we're looking at a vertical slice. The colors here show the rest mass density. So red is high density, blue is low density. White regions show really low density regions. When we run the simulation, what we see is that the disk accretes nicely. There are 2 low-density jets that have been produced. And what you see is that these jets apparently die out after a certain period of time. But don't worry, the jets are actually doing really well. They are disappearing because we're looking at the slice, and the entire system is precessing away out of the plane of the movie. So these jets are still there. It's just they don't intersect the slice that we're plotting them in. And we would like to work with the visualization people here to actually make a nice 3D movie of this. What happens when we try and cool the disk such that it becomes thinner? Would this disk gain ability to align like we expect theoretically? And this is what we're doing here. We again have a tilted disk, but the thickness that we're going to cool this disk to now is going to be 10 times smaller than was before. It used to be 0.3, now it's 0.03. This is the thinnest disk simulated ever, as far as I know. So let's try and look what happens. The cooling causes the disk to collapse pretty fast. You see the disk becomes really thin. At first, we find that there is an aligned part of the disk, but it's initial transient. It disappears. And then in the end, what we see is that the disk goes into the slow motion dance, which we already saw, which is the precession. This is the first simulation of a tilted thin disk in the nonlinear inclination regime, where the inclination angle much exceeds the aspect ratio, the thickness of the disk. What happens if we try to tilt this disk by just a little bit, comparable to the disk thickness? And what we see here is, in fact, the disk that was tilted by about 10 degrees actually becomes very much aligned. So this is perhaps the first demonstration in a general relativistic simulation of Bardeen-Peterson type alignment. These simulations used effective resolution of about 2,000 by 1,000 by 1,000 using 3 AMR levels, and so did the previous simulations. Finally, what happens if we try and make the disk self-consistently? Here we put it in by hand as an initial condition, but we expect that in a tidal disruption event, as the star comes to the black hole, gets torn apart and forms a sausage, and the sausage comes back and feeds the black hole, a disk will form. So what we did here, we asked our collaborator Eric Coughlin from Berkeley to simulate the first passage of the star near the black hole where the cell gravity is important, such that the star flies away and forms a sausage. And this is the sausage that we take from his simulation and feed it into our code. Again, this is a zoom in, and this is a zoom out of the same simulation. And color shows density. Once we run the simulation, we see that interesting dynamics is happening. The stream that goes around the black hole self-intersects and self-disrupts, which, as far as I understand, was seen for the first time. And this would definitely contribute to the formation of the accretion disk more efficiently. It's a big problem in our community to understand how the disks form. This is the first simulation of a stellar disruption by supermassive black hole on a parabolic orbit. These is a bunch of technical terms that probably make sense only to 4 people in this room, but suffice it to say, it wouldn't be possible to simulate this, or we would be able to simulate just one simulation like this using our entire Blue Waters allocation. This is in fact what we propose to do. Using the AMR and local adaptive time stepping, we can run now tens of these simulations, which opens up completely new capabilities of understanding these natural laboratories. Let me wrap up with giving you some ideas about the broader impacts that this effort has led to. This is me giving a public talk at Berkeley. People hopefully look very interested. We also giving lectures at various summer schools. In fact, I'm going to be giving a lecture next week at a summer school in Brazil, and I would like to advertise the summer school that I'm co-organizing in Moscow in July. If you have students who are interested in computations, please direct them to astrosoma.ru. Even though the application deadline has passed, we are looking out for strong students or postdocs who are interested in attending the school, so please encourage them to register. This is my conclusion slide. We're trying to revolutionize by using the GPUs and the acceleration that they provide to attack the hardest problems, or perhaps some of the hardest problems in the accretion, the black hole accretion. Here are just a few examples of the breakthroughs that we were able to achieve in the first year of our Blue Waters allocation. We were able to run simulations that were at the resolution of 1 billion cells, which as far as I know is the highest resolution ever in our context. We were able to see the formation of jets from tilted disks for the first time that were following the precession of the disk, both in thin and thick limits. We perhaps have seen for the first time the evidence for Bode-Peterson alignment of thin disks in general relativity. We are able to simulate for the first time a parabolic encounter between a star and a black hole for realistic black hole mass. It's easier to simulate it for small black holes. We, for the first time, did it for a realistically big black hole. And I also wanted to advertise that I'm moving to Northwestern University in the fall. And if you have students who are interested in computations or postdocs, please direct them to me. I am interested in expanding our group. We definitely would need more hands to help us finish all of this great science. Thank you so much.